Welcome to breadboarding. In the previous video, you'll have seen me introduce the Nanocomp 6809 computer, which was based on a design which was first published in 1981 in Wireless World magazine. What we're going to be doing in this video is building out the basic CPU clock and reset circuit on the breadboard and do a basic test to check that the address lines are incrementing in the way that we've talked about in earlier videos. So here's a printed out version of the schematic, which I've stuck together with 2 bits of paper to make it a bit easier. So in addition to this sort of standard breadboard here, what I'm also going to be using are a number of tools. So there's the wire strippers there. So these are my preferred wire strippers. Flat nosed pliers, so that there's no grips on these, but it's much easier, I find, for gripping wires and things. So there's no serrated edges on there. And then a good pair of wire cutters that can cut really close to the junction. And from a point of view of which components, I prefer to try and look at the components first. So in this box, what I've got is my pre-cut selection of 4-hole and 3-hole jumper cables. So these are the ones that we'll be using for the power rails and things. I've also then got some pins for my reset button riser card. So that's a little card for putting the reset button on. To start with, we need to put a reset button on here whilst we're building the circuit, because the main reset button goes on the keypad and we won't be building the keypad for a little while. So we'll solder that together. We've got the original 6809 processor. That this is the one I bought back in 1981, and we can even see on the code here it actually has 8124 MC6809P. And on the other side, this is one of the later ones I bought more recently. It's got an 86 code on it. Now, it's really important when you're buying these. There are 2 versions of the Motorola 6809 processor. There's the standard 6809P, and there's another version, the 6809E, quite often then with a P on the end as well. So you only want the E one if you're going to use external clock circuits. So for example, on computers like the Tandy color computer and the Dragon 32, because it used some of the chipsets for handling dynamic memory and things, then they use a 6809E. And I made the mistake of ordering some of these, so I actually have about 2 6809Es that I bought by mistake. And needless to say, they won't work with this circuit. So make sure you have the correct chip, and we'll be using the original one that I got back in 1981 to see if this works. Then there's the various other components. We've got a couple of capacitors, the various resistors for pull-up. There's a 4 megahertz crystal and a few other bits of wire and things that we'll be needing. So as the advantage of looking at your components first is it just means that you don't get distracted as you try and find things as you go through. So what I'm going to do now is to move the camera, zoom that in, and then we'll start building this micro. Okay, we've zoomed the camera in. Now, the one thing that I should have said earlier is one of the most important things I found for making these sorts of projects more successful is using chip labels. And my hints and tips video, which will be in a video after this, will cover this in more detail. But there's a sheet of chip labels that Grant Searle's website has got, and I downloaded that from here. And in particular, there is one for a number of processors, the 6809, the 6502, Z80 being some of them. And what I'm going to do is just cut this out and stick it onto the top of the processor here, and that makes things much easier and much less likely to make mistakes. So I'm just going to cut this out. So I'll probably speed this video up as we go through. So there we have the chip label. Here I have the chip, and all we're going to do is take a glue stick. So this is a Pritt stick in the UK. Use the glue stick, put some glue on the back of the label, and then just carefully stick this onto the chip and try and make sure we line up the pins as best as possible. It normally doesn't matter if it's slightly off, but the closer you can get it, the better it is. And this is also where you'll find out if you've printed these out at the wrong resolution on the printer, then you may very well find they don't quite line up here. But generally that's pretty reasonable. So if you've got the chip labels on like that, it just makes it so much easier. You're much less likely to make mistakes. It doesn't eliminate mistakes, but it makes it much less likely. So what we're going to do now is to start putting the chips and wire things up. So the first thing you're going to do is to take chip. Now I have earthed myself here. I do have a wrist strap, an earth wrist strap, but generally during the summer there doesn't seem to be too much static around. During the winter with carpets and things, you sometimes get a bit more static, but I have earthed myself here. I would recommend, if you're handling these sorts of chips, particularly the microprocessors, to take anti-static precautions. Now when putting these into the breadboard like this, you've got two decisions to make. With the wider 0.6 inch wide chips, you normally have only got space for 2 holes on one side and 3 pins on the other side. And in fact, in this particular design, we're going to want to leave because of the number of wires we need around the clock circuits for the crystal, we probably need to have the 3 holes on this side. So, and then the other thing that you need to check is the problem having these gaps in the power rails is that if some of the pins you want to pull to ground or to 5 volts are in a gap, then you end up needing to put a slightly longer lead in there. So again, it makes sense to try and just sort of arrange things so that most of the lines that you want to tie to positive or negative rails are going to be. So we want the Holt, memory ready, DMA all want to go, and we've got VCC and VSS. Yeah, so we just plug this in now. If you've got a new chip that hasn't been in a socket before, you may find that you need to bend the legs so that they're more vertical. Quite often when chips are first come out the packet, the legs are splayed apart a little bit, so you need to press this in. So in general, with all these things, what I tend to do is use these flat nose pliers to put the wires in, because my fingers are a bit wide and fat, and so it makes life a lot easier to pick up the wires from this. So we're going to wire this up. I have got a couple of check marks in this. I had a problem with the video. I have to repeat this, but I'm not going to print out the schematic again. But as I will be saying in my hints and tips, what I find it useful to do is to tick off the leads when we actually connect them. So the first thing we're going to do here is to tie in the power rails. So first power rail we have here is VSS. So I tend to use the pliers, these flat faced pliers, which don't have any grip on them, tend to be easier for manipulating these sort of jumper wires. And then we'll put in the VCC. Now I do have to be careful here because I'm looking at this from an angle, so it is actually quite easy to end up putting these in the wrong. So in fact I will look from the top, so I've done that wrong there. So let's just look from the top. There we go. So we got VCC to +5, VSS. Again, I've looked at this from the side. So looking at it from the top, we can now see that VSS is in the correct place. Right, so what I'll do now is wire up the other +5 lines. So this includes Holt. The Holt goes to 5 volts. We'll also do memory ready. And by doing the ones which are tied, okay, memory ready doesn't quite tie up with this, but the problem with these is you can't always get all of them to line up. And then we'll do the DMA one. This also means when you do the ground and the +5 wires in, sometimes this helps to make things a little bit easier when you come to wiring the other things. So we'll just check these off. So we've done the DMA, done memory ready, we've done the Holt, and we've done VSS, and we've done VCC. What we'll just do now is to finish off the capacitors for the power supply. So polarized capacitors, we need to make sure that the negative side goes in the correct polarity power supply. So we're just going to put this between the negative and the positive here. So generally these the capacitors for specific chips generally want to be as close as you can get them to the power pins, and in general, let me just put that in there. I generally don't include the decoupling capacitors on the circuit diagrams for breadboards, just because I tend to put them in for every chip anyway, and it just clutters things up. But obviously, if you were making things into printed circuit boards, you would almost certainly need to include them, otherwise they wouldn't end up in the final design. So what we've done here now is we've got the power, we've done the decoupling capacitor, we've got those hooked in, and we've also got a 0.1 nanofarad decoupling capacitor. We've done a Holt, memory ready, and DMA. So now what we just need to do is the reset circuitry. So this is another 22 microfarad capacitor. Again, this one we have the negative side, which needs to go in. Make sure I look at it from the top and I get it in the right holes. So just put this in from the side here. Okay, so this is going from the negative rail to the reset line, and then this 5.6K resistor needs to go between the reset and 5 volts. And since the memory ready has 5 volts next to it, we're just going to plug that in there. So, right, let's just tick those off. Right, we've done those. And what we've got left now is the clock circuit. So this is a crystal and 2 capacitors. So there's a 4 megahertz crystal, which you may or may not be able to see. Now the problem with the crystal is that the 2 crystal pins on the chip on the processor are next to each other, and the crystal is has an extra pin in the middle. So what I end up doing here is we need to extend one of the crystal pins to go up an extra line or 2. So what we're going to do is to have the crystal going up to row 21. I think this would show, so this is row 21. This will be going here, and what we need to do is to put in a wire that goes from this crystal thing there to that row. So what I'm going to do is get my cutters, strippers. We're just going to bend that, and then this is where you follow the Ben Eater videos. This is where you can then just sort of work out where you want to make the cut. So in the crystal, we want it to go to here, but we need about another 1/4 of an inch beyond that. So that's where it needs to go, 1, 2.5. So cut it about there. Traditional cutters. So now we just make a bit of wire. And so we need to take the crystal extal line out to row 21. Okay. Now leave the wires a little bit long at the moment. We might trim them once we know everything's working. That means that the crystal is in fact across this line here and this line here, and now we need to put two 22 picofarad capacitors between the crystal pins and ground. So again, we need to make sure we are getting the right pins here. Now again, the frequencies he's running at, we definitely need to chop these down, but for now, just to get it up and running, we will. So we've got this one here, and ground, and there we go. So what we've got there is effectively the crystal goes between the two pins on the processor, and then the two 22 picofarad capacitors go between the crystal and ground, So in fact, you can see that we've done that there. So it's a little bit fiddly. This is probably the more tricky part of this particular circuit, is getting the clock circuit to fit. One of the alternatives we could do is to put the clock circuit up here and just feed it into one of the inputs here, and that might be something we'd do, but I wanted to make this as close to the original design as possible. So we know now that we've actually got the two capacitors are connected to the ground, two capacitors are connected to those bits there, and we've also connected those to there. So let's have a little bit look at what other things we've got. Well, we've also got the interrupt request lines that need to be tied to 5 volts here. So let me just get these resistors, and we'll put those in roughly. Again, I won't cut these to length for now, and all we're going to do here is for these to be taken to +5 volts. So we'll do that for the non-marketable interrupt, +5 volts. Okay. And then the interrupt request and +5 volts. You can see that if you don't really want to start chopping the leads down until you've got the layout sorted out, because sometimes you might need to move things around a little bit. And then the fast interrupt request we also need to tie to +5 volts. Let me just move these around. Let's put this a little bit closer to home. You can see that obviously, depending on where you put the decoupling capacitor, there's a trade-off between putting the decoupling capacitor in the right place and putting these pull-up resistors. So I think we just about got this. Okay, so they're a bit long and straggly for the moment, but as we've shown before, once you've got the circuit working, then you can just tidy it up a little bit. So the only thing we really need to do now is to set the data lines to be, if you remember, the no operation code was 12 hexadecimal. Now, what I've found, what I've done is build a simple circuit here. This basically just has some resistors and a dip switch, where all the dip switches are, when they're on, they pull to 5 volts. When they're off, they're pulled to ground. And then these 8 inputs go through a buffer chip and then drive this LED display. And the reason why I do this is just it's easy for testing things initially. And what I've got here, you can see on here the digits you've got here are 1. We've got the second and the 5th bits are set. So this will be 2 and this will be 1 0. So between the two of here, we've got 1 2 hex. So this is the more significant bit, That's the first bit of the second hexadecimal digit, and this is the 2 in the bottom hexadecimal digit. So effectively, this means that this is the no operation code. So all you need to do is to hook up. This is the lowest end, so this will go to D0. This will go to D7. Again, one of the problems of all these sorts of things is that whether you're dealing with computer-based systems that always seem to count from 0, and so if you've got 8 of something, it will go from 0 to 7, or if you're dealing with things that are numbered from 1 to 8. And there's always this trade-off when dealing with electronics, again, A1 to A8, whereas when you're looking at the chip itself, you're dealing with D0 to D7 and A0 to A15. So there's always a potential confusion to get your number ranges sorted confused. And I must admit, I tend to work with 0 to n-1 tends to be the way I'll work, just because that's the way how most software works. So what this now means is that if I want to set all the data lines to be 1, 2 hexadecimal, so the no operation code, all I need to do is to wire in the plus and minus lines on my little test rig here. And then I just need to make sure that I wire in these in the right order. So we can put, again, make sure we look in from the top, D0, D1, D2, D3, D4, D5, D6, and D7. Okay. Now again, what you could do is we could just wire all of the most of the lines to the ground rail, and then just the D1 and D4 would be a resistor to plus 5 volts. But the advantage of this is that we can change the values quite easily, and I've found this the easiest way to do this. Now, what I'm also going to do is, because we're expecting the address lines to be cycling quite rapidly, so A0 is going to be working at around 250 kilohertz, but the top address lines, so A15, A14, and A13 should be visible. I won't wire in the other ones because they'll be going so fast you won't actually be able to see anything. So what we've now done is we've wired up the data lines to have 1, 2 hexadecimal, which is a no operation code. I've wired in the power supply for my little test board, and what I'd expect to see here on the lower board down here, expect to see this segment, which is on A15, probably we should be able to see that flickering. This one might be able to see it flickering. This one probably won't flicker at all. These other ones will probably end up being on, just because by default the buffer, if it doesn't have any input, will tend to pull high. So expect to see this one flashing, this one possibly flashing, and this one slightly dim in that it will be flashing, but very, very fast. Okay, so all we need to do now is to hook up the power supply. So to do this, to start with, I'm just using the Ben Eater style USB cable that has had the ends chopped off. So this is a normal Type A cable, chopped off the ends. The data leads I have actually left and tied up, insulated in case I need them. And then I've just got an old iPod charger. So this is theoretically capable of doing 1 amp, which is going to be more than enough for what I need to do here. So I'm just going to plug this into the power strip. And we will make sure we plug the leads in correctly. So I put the positive on that side and the negative on that side. It's always worthwhile double checking that, because I suspect it wouldn't do the chips much good putting them in the wrong way around. This is one of the advantages once you've got a slightly more stable environment. Just down so you can see it. So you can see the power supply pins are in there, and we can also see the values on here. Right. So now what we need to do is to plug it in and see whether anything starts glowing or whether anything starts smelling rather unpleasant and burning. Right, great. So we've got success here. Might not show up very clearly on the video, but this initial one here is quite clearly flashing. This second one here is not doing terribly much, but this other one here is definitely flickering. So you can see these are flickering, but it does look like it is clocking. And what I'm going to do now is sort out my reset button, and we're also going to hook up a logic probe. So this is Kinxt logic probe. So this has 16 lines, and what I'm going to do is to hook this up, and we'll be able to look on the logic analyzer and to see what exactly the address lines are doing to see if everything's working. Okay, so this is my little bit of Vero board, strip board that I have created for soldering these push button in. The trouble is that push buttons there, the legs on them will just about fit in the breadboard, but they do tend to strain the holes, the clips inside the holes a little bit. So I think it's generally going to be safer to use this sort of nice circular pins to plug this in. Now, the first thing I just wanted to do is make sure that I got the pins the right way around. So by default, my meter is set to, my meter is just set here to give an audio signal when there's a circuit. So when we have the two sides like that, then those are always connected two side by side like this. When we press the button, you should get, there we go. So only when we press the button. So I've got the contacts the right way around. Just need to make sure that when you're hooking these up that you know which way around the contacts are going. So this, I've already drilled out the holes, so the holes here need to be a little bit larger to fit these leads in. So we're just going to actually plug that in, and what we're going to do is to put going to put 2 pins in either side. We'll probably take the middle pin out to avoid any confusion, and we're going to solder all that together. Okay. And that side, we'll just do the other side as well. Here's a little bit fiddly. Right. Now what we're going to do is to take this, and I found it easiest to use an old breadboard I don't use much anymore. This K&H one down the bottom here, and we're going to cut 3 pins carefully. Hopefully it doesn't break the. Okay. Okay, so I've taken out the middle pins out of these. Might need to tidy up the soldering on here. It's a bit difficult to do soldering with a camera above things. And then what I'm going to do here is I'll leave the longer pins for like this. What I tend to do is just then put this in here, and then makes it really easy to make sure you've got the pins the right way. So There we go. Okay, so now we need to do is to solder. Right. Okay, it's not the cleanest of jobs. I'm certainly not going to get a job as a professional solderer. Another good reason for using breadboards and not making things for PCBs. Right, so the only thing I'm going to do now is, as I said, it's always a good idea to test things as you go along. So if we put this into breadboard here, and I've got my test meter, and I've got my power meter here, my is my EEV blog Bryman multimeter. You can see if there's a connection, then we're going to get thing. Now we'd expect to hear a beep when these pins are connected here. Okay, we expect that. We expect that, but when we're plugged in this way, we only expect to get a sound when we, yep. And let's do it on the other side. It should be exactly the same on the other side. It's always a good idea to test things before you put them in with everything else, because there we go. Okay, so it's very simple thing, but there is a site I found that makes little printed circuit boards which are double-sided as well, which will probably make this a little bit easier to, rather than having to solder everything on one surface. Double-sided boards would allow you to solder on this side for the switches and for this side on the pins. So hopefully we'll order some of those, and I'll do that in a future video. So we've made our reset button, and so what I'm going to do now is we will just wire this in. What we're going to do here is, for the moment, we'll just wire it in any old place up here. So we just need to have one set of pins connected to ground. So we need a long black one. So all I'm going to do is to tie. What I'm going to do is to tie one side to ground, and then make sure I'm looking on the top we're using the right one. Okay, so that is one side is tied to ground, and then for the moment I'm just going to use a fly lead to go from here to go to the reset line, because at some point we're going to need to hook in the reset signal into some bus lines, but for the moment. So that should now allow us to do a reset as and when we want to. So we've now built our breadboard CPU clock and reset circuit, and in the next video I'll be hooking up a logic analyzer to the board, and I'll be looking in detail at the address lines and the control signals that drive the Nanocomp 6809. Thanks for watching. Please hit subscribe if you don't want to miss out on future videos. Thanks.